So unit three still. Right underneath where you guys said what is a force? I want you to write this down. Types of forces. So today we're going to talk about types of forces. We're going to talk more about free body diagrams. I know that kind of quick yesterday, so we'll kind of expound on that a little bit more. Then we have some examples I want to work through. So types of forces. The first type is called a contact force. Now, if I say something's in contact, that means that they are touching. Okay? So a contact force is a force exerted by objects that are touching. Okay? So there's a force exerted by objects that are in contact, okay, or touching, right? So, what's an example of a contact force being exerted on you right now?
This table, the chair.
The chair, the table, right? Some of you guys are laying on the table with your elbow. The table is exerting an upward force on your elbow, right? You guys are sitting in the chair is exerting a force
The floor.
on your bottom, right? You guys are your feet are on the floor is exerting a force up on your feet, right?
Yeah.
Those all happen because you are
In contact with them.
in contact with that object. You don't need to, but if you stood up right now, would the chair still be in contact with you?
No.
No. Would the chair still be applying a force on you?
No.
No. Okay? We know that because when you stand up, the force felt by your feet does what?
It's heavier.
Gets heavier, it increases, right? Because when you're sitting down, your feet don't feel as much force, and that's why it's called taking a load off, right? Everybody sit down and say, hey, take a load off. You sit down and, you know, take a okay. You guys know what I'm talking about?
Yeah.
No, not that, Jameer. Okay. So, then when you stand up, right, when you stand up, you're now carrying your whole body again, so all the force your feet are experiencing the force your body. When you sit down, we know the chair exerts a force on you because your feet are feeling less force. Does that make sense?
Yeah.
Okay. So by standing up off the chair is no longer in contact with you, so it no longer exerts a force on you. Does that make sense?
Yeah.
Okay. So contact forces are forces exerting by objects that are in contact. So what are some examples of these contact forces? Any idea? A push.
A pull.
A pull. A pull is a contact force?
Yeah.
Okay, because I'm pulling on an object. Either I'm pulling on a rope, which is attached to somebody, or pulling on someone's shirt, right? Right? Pulling on someone's arm. That is all a pull. Now, if the pull goes through a rope, okay? If the pull goes through a rope or a string, then what's the force called? Tension. Okay? The pull goes through a rope or a string, that's why it's called tension. If anybody plays guitar, all right, sometimes you need to tune the guitar by changing the tension of the strings, right? You're changing how hard the strings are being pulled by the bridge, or not by the bridge. What's it called right next? Is it the bridge?
What?
Well, the neck's at the top and the bridge at the bottom. Either way. But you're changing how hard the string's being pulled, and that changes the pitch. Right? My experience with guitars is very limited. Alright, so we have a push or a pull. Pull pushes can be called tension, or pulls can be called tension. What's another contact force?
Football.
A punch. A punch is like a push. Okay. Football is a contact sport. What are some other things that involve contact?
Catch.
Okay, catch is kind of like a push. You're pushing out to stop it.
Wait.
What? Running?
He's talking about to right. Well, you're just pulling me.
Oh, to right, you're kind of pushing on the pencil. Okay.
Pulling.
Anything else? Or pulling on the pencil, depending on how you look at it.
Not really.
Now, some of these pushes and pulls can be recategorized into different words. Okay? Right now you're sitting on your chair, right?
Yeah.
Your chair is pushing up. Okay? Now, the angle the force of your chair makes with the chair, the angle the force makes that's being applied to you, the angle it makes with the chair. Does anybody have any idea what angle that might be? It's a 90-degree angle, right?
Yeah.
If I'm sitting on the chair pushes up perpendicular to the surface of the chair, right? Right? If I push down on the table pushes up on me perpendicular to that surface. Okay? That type of contact force is called a normal force. A normal force is a force that's perpendicular to a surface. That's perpendicular, not just a surface, but to the surface applying the force. I'm gonna use the perpendicular symbol. That's perpendicular, right? That's like a P. Okay. Force that's perpendicular to the surface, applying the force. So the force the chair exerts on you is a push, but it's called a normal. It's called a normal force because it's perpendicular. Okay? Just like if I look at Cassandra's book on her table. All right? The table is applying a force in the book. Which way? Up. And that force is perpendicular to the table. That's called normal force. Now you're probably wondering where does the term normal come from? Well, remember when we were talking about curves earlier, last chapter?
Yeah.
And we talked about a line tangent. If I draw a line tangent at this point, it's parallel to the graph at that point, right? Well, the opposite of tangent is normal. Okay, it's perpendicular to the graph at that point. Okay, it's just an old geometry term, right? Normal just means perpendicular. That's where it comes from. All right. Any other forces you might know that involve contact? Say my hands are cold. Heat, temperature. I want to warm them up. Friction. So if I rub my hands together, right, they warm up, right? Because of the friction between my hands. Now, if my hands aren't touching and I rub them together, right? I'm rubbing my hands together without them touching. Are they warming up? Are they warming up?
Yeah, a little bit.
A little bit because of the air friction, right? But not as much as if they're touching. Okay?
Gets your blood.
You can always go to heat.
Gets your blood moving. All right. But in order to get that friction between my hands, they have to be touching. So friction is a
Friction force.
contact force.
Good job.
Does walking count?
Well, walking isn't a force.
Well, no, but I mean,
There are lots of forces acting as you walk. As you walk, your feet hit the ground, right? If the ground was slippery, when your foot hit the ground, it'd slide, right? So what's happening is my foot hits the ground. I'm now going to push on the ground that way, opposite my direction. I'm pushing back on the ground. The ground then will change the force and pushes me forward. And it actually uses friction. Okay? The friction force from the ground, my foot wants to slide opposite the direction I'm going. So the friction force from the ground is in the same direction I'm going. That's why you want shoes that have good grip when you're playing football or basketball or wrestling or tennis or volleyball. Right?
Those are called.
Motocross.
Cleats or new basketball shoes that still have like the little circles on them. Right? If you have the basketball shoes where all the stuff is worn off the bottom and you kind of slide all over the place, right? It's really fun to watch. I think it'd be kind of funny if you gave everybody old basketball shoes and they ran around and slipped all over the place.
That's called getting cross.
Yeah. Kyle, it's just your excuse. My shoes are bad, right? Okay. All right. So friction's our contact force. What's another contact force? My daughter's favorite book is 5 Little Monkeys Jumping on the Bed. Well, maybe not her favorite, but it's one of the ones I like to read her because she always, whenever she sees the monkeys jumping, she always goes, no, 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 and yells at them. It's funny.
Gravity.
Right. Well, not gravity, right? But gravity's one part of the jumping on bed, but the other part is when the monkeys hit the spring or hit the bed, they compress the spring, right? Okay? That spring only applies a force to the monkeys when they are in contact. Once the monkeys leave the spring, does it still apply a force to them?
No.
No. So another contact force can be a spring force. Or the force from a spring. Okay? Now, friction. Last hour we had a long discussion about friction. There's a part of friction that I was hoping somebody would bring up, and somebody kind of did, but it is air resistance.
Yeah.
Right? Air resistance. Now, when I say air resistance, do you guys think that's a contact force or not?
Yes. The air particles. The air
What?
particles are hitting you.
The air molecules, right? The air particles. As I walk, what gives me air resistance is the air particles hitting me. Okay? So air resistance, even though we can't see the particles, the way it works is as I'm walking through the room, those particles hit me, and that's what causes the air resistance. Okay? So air resistance, a type of friction, is still a contact force. Okay? Does this make sense about contact versus non-contact?
Yeah.
Now, forces in general are represented with an F. Okay? And some of these have special abbreviations. Like normal force is Fn. Okay? Friction force is F little f. Okay? Or you could write it F mu k or F mu s, but that we'll learn later, so I'll just erase that again so it doesn't confuse you. Okay. Okay, so force friction. You could also write FAR because the AR stands for air resistance. That works as well. Now springs, sometimes springs they'll write FK because K is a spring constant, or they can just write F spring. Okay. If you ever want to denote a force, you can always write the force and then what's causing that force, and that'll kind of remind you. So like let's say like Jose is pushing on Jameer, all right, you can write F Jose. Okay, not like that.
You did that on purpose.
I did not. Like that. All right, and that'd be the force that Jose is applying to Jameer. Okay. My goodness, you guys take everything and go the wrong way with it. All right. Any questions? Any questions? Now, how do we represent these forces? Symbols and stuff.
The line.
The lines.
The dots.
Free body diagram. Oh my goodness, don't start that one. Oh, I forgot a type of force. Oh my goodness. I have one, but no two. I figured someone would say something. Okay, the other type of force is a
Non-contact.
it's a field force. Okay? Now, those of you that are avid Star Wars watchers or maybe the Star Trek watchers, you might know something called a force field, right? Well, right now, you are experiencing a force field. Every one of you. Okay? What? A magnetic field is an example of a force field. Okay? A gravity field. Right now, you guys are in a gravity field. The gravity is exerted by the Earth on you. Okay? As long as you are within the Earth's gravitational field, then you experience the force of gravity. Okay? So, this gravity is a great example of a field force. If I have this marker, right? I have my blue marker. Jameer, stop talking. Shh. Okay, so I have a blue marker. Is this blue marker experiencing the force of gravity right now?
Yes.
Yeah. How?
Because
you're
it's trying to pull it down.
It's not moving up.
It's trying to pull it down, but
Okay.
you're so muscular.
So is it
You're
feeling,
holding it up.
is it feeling the force of gravity because my feet are touching the ground and gravity's kind of going through me?
No.
No. It feels the force of gravity because we're close to the
Earth.
Earth. So when I let go of this marker, what happens to it?
It goes down.
It's going to the Earth.
It falls towards the Earth, right? The Earth is not in contact with the marker, but the marker still feels a force. Right? That's called a field force. Right? So a field force are non-contact forces. They are forces exerted without contact. Okay? So one example is gravity.
Magnetic.
One example is gravity. What's another one? Magnetic. Good.
Taking my words.
Your word?
I don't see your name in it.
All right, take it easy, guys. Okay. Magnetic is another field. Okay. Football field, different type of field. Okay. There's one more field force I expect you guys to know at this point. What does it start with? It starts with an E. What is it? Okay. Electric.
Good job, man. Good job.
Electric.
Something that experiences electron fields are electrons, right? Electrons stay near the protons of an atom because they're attracted electromagnetically, right? Because the electrons are attracted to the protons. So the electrons will stay around the protons of the nucleus, right? All right. See, you know about your croutons, right? All right, now, magnetic. So way back in the old days, people used to pass themselves off as magicians because off as magicians because they knew how magnets worked. Okay, for example, they might hold something in their hand like this red magnet, and they might bring another magnet closer and say, "Look." Oh, put the wrong one down. Okay. They might bring another magnet closer and say, "Look."
Hold on, I can't see.
I'm a magician. Okay. I just moved this without touching it. Watch. Okay. Now they might do a better job hiding it. They might like put the red magnet in their palm like this and do something like this. Oh.
Put it
Come
in
on,
a
come on.
glove.
Oh, I need stronger magnets.
Or put it
Or put it in a glove or something. Here we go. Here's some stronger magnets. Okay. Ready?
Try the blue one.
Oh, it's a negative.
Oh. Failure. But you guys get the idea, right? Hey, you get some better magnets. All right. Last time they worked great. I think I used the smaller ones. Here you go. Here, this little white one. Guys, the white one and the red one. Come on. Oh, there it goes. Okay. So they might do something like this. Nope, flipped over. Come on. There you go. And they might say, look, I'm a magician.
You are.
Never mind. A bad joke. All right. But either way, they get away with magnets as being magic, because what the magnets exert is a magnetic field on each other, which apply a force to the other magnet. Right? So, do magnets have to be in contact for there to be a magnetic field, for there to be a force between them? No. Okay. When the one magnet gets close to the other one, it experiences the magnetic field, and then that causes the attraction between the magnets. All right. All right. Any questions?
Yeah.
Yes. What is that?
So that means that magicians don't really make
They use physics.
I'm not. I don't want to like ruin anything here for you, but typically magicians are just really sneaky individuals, and not in a bad way. Not in a bad way. They're just sneaky in the sense that they can have you look one way and then have something else go on that you're not paying attention to.
You ever seen that one movie?
What about Chris Angel? Keyword there. What'd you say? Begins with
Chris
an M.
Angel is
Yeah, begins with an M.
art of graphics
Movie.
and
Okay. Movies are different than life. Okay. Chris Angel. Most of his good magic happens
through graphics.
on TV.
Yeah, it's graphics.
Okay. They do stuff with the TV, so it makes it look like he's doing things. Okay. Now he is a good magician. He's a very good entertainer. I'm not gonna lie. He does entertain. Okay. But the magic he does is more sleight of hand. He's doing things. He's distracting with one thing and then switching something to somewhere else. What? Sleight of hand. He gets you thinking about something else. Then he. Doesn't really float. All right, we'll get into that later. Okay, let's get back to the physics. All right. So, any ideas about contact forces and field forces? Okay. Now I'm gonna get like a nasty email from Chris Angel. You know, why are you talking bad about me in your class?
But he made
Probably
Shaq
not.
float.
All right.
He made Shaq
I
float.
don't think he's gonna watch it.
On
TV.
TV. There you go.
That's a big dude.
Okay. So, field forces, contact forces. Any questions? Any questions? All right, I'm gonna use the spacer right here without contact. Now, how do we represent forces? What did we say? Okay, we talked about it a little bit yesterday, but representing forces. Scott, you have any questions?
What?
You have any questions?
I'm straight.
Okay, you just want to make noise. Just make noise. Alright. So, representing forces. One way we represent a force is with a free body diagram. They're not very costly.
How much were they?
They're usually cheap, really cheap.
You are a
You're so
funny. Good joke back.
I know. All right. So representing forces, we just call a free body diagram. Now, in the past, I told you that physics is for doodlers. Okay. The reason why I told you that is because we are going to draw a picture of a situation.
They have a song about that.
What?
You should look it up.
About free body diagrams?
It's called FDB.
No,
Yeah, I don't
not
think.
FBD.
It's FDB.
Okay.
Look it up.
It's not this.
It is.
Free body
Yes,
diagram,
FB.
pal. Your
Where's
word's
that?
messed up.
Just look it up.
Okay.
Yeah.
Kyle. So, let's say I have Cassandra's physics book sitting on the table. Good, she hasn't moved it yet. All right?
We did this yesterday.
I know we did this yesterday. Kind of. It was at the end of the hour and some of you weren't paying attention completely. Katrina.
Why do you have to record in our hour? Don't we have to be quiet?
You don't have to be quiet.
You should have done it first hour when they're sleepy.
You don't have to be quiet.
It's always like a
Jameer, stop talking.
video.
Okay. So,
You don't have
Yes,
to be
it
quiet
was.
as you're
Well,
talking.
you're
You can be
recording?
quiet.
What if you would have told me now?
We don't have to be quiet.
Hi, people of YouTube.
there you go. Nice job, Rex. All right. So,
Shout out.
there's my physics book. Actually, Katrina, I'd rather you ask questions because the questions are more helpful than anything I have to
So
say.
you know if we get off like topic a little bit, we can get off topic.
Yeah, I don't get off topic in the first hour either.
Yeah.
Okay.
You get off topic all the time.
So, there's my physics book, right? Or Cassandra's physics book. What forces are acting on the physics book?
Oh, that's a table.
Gravity and
The table.
an upward force from the table, right? Now, where do those forces act on the book?
Down and up.
Up and down.
Okay. The book is in contact with the table, so we could say those forces are acting all over the bottom of the book, right? Right? Now that's going to make our drawing very difficult if I have to draw forces all over the bottom. Okay? So what we do is we pick a spot on the book that we call the center of mass. Now where in this book is the center of mass? What do you guys think? The middle. What feature of this book might be close to the center of mass?
Where it says the white.
This white part right here? Okay, where it says authors. Okay. So if I could somehow support the book at that point, the book should stay supported, right? If I could somehow apply a force right there, I should be able to hold the book up, right? Okay.
No.
So I'm going to apply a force right there.
Sides.
Just down the middle. Oh, just down the middle again. Alright, there we go. So I'm applying a force right at the middle of the book. Right, you guys see that? Okay. And I'm supporting it. So my upward force is right in the middle of the book, and gravity is acting straight down from the middle of the book. Okay? So this is the reason why when we draw free body diagrams, we can draw our forces, instead of drawing the forces acting all over, we can have them acting where?
At the middle.
At the middle. Okay? It's a lot makes physics a lot easier if we assume all the forces act at a point called the center of mass. Okay, I got outside the center of mass and fell. Right? So if we assume all of our forces are acting at the center of mass, it makes our free body diagrams a lot easier to read and easier to draw. Okay? Cal, what's up?
You know how people balance stuff on there?
Yep.
Does that have anything to do with this or no?
Exactly. Okay. The center of mass of an object is usually in the middle. Is usually at the geometric center of the object. Okay. When I say the geometric center, it's like if I were to draw lines of symmetry in the object, where all those lines cross, that's probably where the center of mass is. Right. So the center of mass of this marker is going. If I draw a line of symmetry this way, it's right down the middle. If I draw a line of symmetry this way, it's right down the middle. So where they intersect is right there, right? So that spot would be considered the center of mass. Okay. Now I'm assuming that this marker is equally weighted. All right, it has the same amount of weight at the top and as it does at the bottom. All right. Now the book is a good example of that because the book is pretty much equally weighted except for the binding. All right. So my fingers, what I was holding, were really a little bit over here to your guys' right. Okay. Because that way I was taking into consideration the binding. Okay. But if this whole thing was equally weighted, had the same density throughout, then the center of mass would be right in the middle, where all the lines of symmetry intersect. Okay, does that make sense?
Mm-hmm.
So now if you're trying to balance something on your hand, right? Like if I'm trying to balance this marker on my finger, okay, then I want to make sure that my finger is directly under the center of mass. Okay? I know. Thank you, Rex. Does that make sense? So if you want to balance a broom on your hand, like a big push broom, right? You want your hand right underneath the center of mass of the broom, which is close to the head of the broom, right? Which kind of makes it difficult to keep that. Right? Does that help?
Yeah.
Okay. Now, once that center of mass gets out over the edge of your hand, what happens? It falls. Right? That's the same thing with cars. Everybody remember those commercials? Wider is better. I think Mazda was doing those commercials. You guys remember those ones or no?
Sure.
They would say wider is better. Yeah. Okay. Because the wider a car is, the less likely it is to flip. Right? Because the center of mass has a longer distance to roll or to get over the edge before it flips over. Same thing like SUVs. SUVs that are on narrow chassis, all right? You guys can probably think of one. Okay, I don't want to throw any belts under the bus today. Chris Angel's enough, all right? The narrower SUVs will flip over easier because their center of mass is closer to the edges. Oh, there's plenty of them. Okay. The narrow SUVs. The SUVs that are on car chassis. Okay. What?
What are you talking about in particular?
Well, there are wider SUVs that you can figure out, and there are narrow ones. All right.
Give an example.
I don't want a lawsuit from Ford or from GM or somebody for saying that their SUV is going to flip over. All right.
What are we gonna do?
All right. So back to center mass. So the center of mass of this book is right there, right where all the lines of symmetries would intersect. Correct?
Yes.
Now, which way does gravity act?
Downward.
Downward, right? So we have a force down. Now this is the force of gravity. Gravity usually write F G. Okay. So over here when you have your field forces, you may want to put a little thing next to gravity and write Fg, so you know that that is gravity.
I'm taking it. Magnetic is FM.
It's actually Fb.
Okay.
Alright. So what else is acting in the physics book? Normal force. Which way is that? Up. Now, how does that normal force compare to the force of gravity? They're equal. How do we know they're equal? Good. So there's this force normal going up that way. Okay. Now, if you are as good of an artist as I am, all right, and you draw pictures like this, and they're not very good, all right, then instead of drawing pictures like this, when you draw your free body diagram, you can just simply draw the center of mass. Okay. And then I can draw the forces acting on that center of mass. And it is the same as this one, except I didn't draw the table or anything else.
It was a buck or...
Does that make sense?
Yes, it does.
What does FN stand for?
Force normal. Okay. Now I will also accept on this one, instead of force normal, you could also write force table. I'll accept that one too. Okay. Any other questions? So, Jose, what do we say the relationship between Fn and Fg were? They're equal. And we know it's equal because this object is not moving. By moving, what word do you really mean? Accelerating, right? We know that those forces are equal because this object is not accelerating, okay? So Fn equals Fg, which means the acceleration of the book is 0. Now, let's say for a moment, give you guys a little bonus that first hour didn't get. Let's say I take another physics book and put it on top of Cassandra's physics book. Okay? Right? So I take another book and I put it right here. Okay? What happens to this normal force right here?
It gets larger.
It gets larger.
It gets larger. Why does normal force get larger?
More weight.
Because there's two of them.
More
Okay.
mass.
So this normal force is now bigger, right?
It's holding up more mass.
Right? Well, I didn't change the mass of this book, right?
But you added
So
more mass.
I know. Let me finish, okay? I didn't change the mass of this book, so does the force of gravity change?
No.
No. What changes though?
The same thing.
Scott, that's what you're getting at, right? What changes?
The amount of mass on the table.
Okay. The amount of mass on the table changes, but what about the force in this book? What's applying another force to this book now? The book on top, right? The book on top is now pushing this book which way? Down. And if they're the same, okay, it should be the same length of the force of gravity. So that black arrow I just drew is the force from the book on top. Right? So I didn't change the force of gravity, but I added another force there because I put the book on top. Right? Does that make sense, guys? Scott, does that make sense?
Yeah.
Okay.
That makes sense.
All right. It does not change the force of gravity. So by throwing this book on top, it does not make the force of gravity act on the physics book longer. Okay? It doesn't make it big. These two down here will equal this one up here. So these lengths are half the length of that. Okay? Because the length of the vector, Reggie, the length of the vector is indicates how strong the force is. Right, Rex? Right, Michael? Okay. Now one last thing, and we'll try out some examples. Last thing is net force. What is net force?
Combined amount of force.
Isn't it when it's distributed?
The net force is the sum of all
Forces.
the forces acting on an object.
And it's the same as adding vectors, right?
Yep, it's basically vector addition. To find that force, we do vector addition. And the symbol for net force, I know it's the last thing, F net. Okay? Not Fn, because if I write Fn, that's normal force. Okay? So F net is the symbol for net force. All right? Any questions? Questions?